We have come a long way since the Wrights faced the dunes and the winds of Kitty Hawk with their first gliders. Montgomery and Lilienthal before them had shaped the wing, but they opened a new dimension to flight. The Wrights developed an airplane with the power of a gasoline engine. This gave the promise of a future in the air that has closed our world around us. And no two people are more than a day or two apart. The initial drive to perfect the airplane came because of its uses in World War I. Speed, range, and carrying capacity increased, and by the end of the war, the airplane became a tactical weapon of importance. Within 7 years, the first regular airmail delivery was begun between Washington, D.C. and New York City. And the first passenger service covered the 8 miles between St. Petersburg and Tampa in a flying boat. Aviation was soon pushing the limits of speed, altitude, and distance. Glenn Curtiss and his R-3C racer, with pilots Cy Bentis, Al Williams, and Jimmy Doolittle, captured the speed record. In the 20s, the Atlantic was crossed many times, and in 1927, Lindbergh did it solo, from New York to Paris. Wiley Post and his Lockheed Vega, the Winnie Mae, set altitude records, and he circled the Earth. The Vega became a record breaker for many famous aviators: Jimmy Mattern, Roscoe Turner, and Amelia Earhart. The National Advisory Committee for Aeronautics led in engine and aerodynamic research. Howard Hughes, a leader for 2 decades in aviation, set a new transcontinental record in his racer, as well as a faster time around the world in a Lockheed Electra. Lincoln Ellsworth made Arctic flights with Amundsen in the airship Norge and explored the Antarctic in the Northrop Gamma, an all-metal, skin-stressed airplane. Admiral Richard Byrd had pioneered polar flights in 1929. In the 30s, the NACA developed a series of airfoils and a cowl around the cylinders of radial engines. Ethan Jacobs, an engineer of NACA's Langley Center.
When I joined the research staff at Langley Field, what was then National Advisory Committee for Aeronautics, I was put in charge of the variable density tunnel, and I saw an opportunity to do some really important investigating of the effects of various wing shapes on their performance. You could replace a wing by a thickness distribution and a curvature. And the real wing was a combination of those two things, and we devised a system that we gave NACA numbers to represent variations in these variables.
Engine performance under the research of NACA's Lewis Center kept pushing aircraft faster and faster, and soon the flow of air over the wing's surface became a problem. They were called shock waves, forming around Mach 1. The efficiency of the wing was disturbed. One of the first aerodynamic fixes was the innovation of the swept wing. Adolf Boesmund.
I was born in a harbor town where we had My father was a harbor engineer where we had ships, and I could see the bow wave of the ships. And they are, of course, a much easier to understand thing. And therefore, by having seen enough bow waves, especially in river boats, where the wave pattern is more similar to the one of sound. In the ocean, the waves are complicated. Every wavelength has a special velocity. But in the river boats or in shallow water, you have a similar thing, but of course in 2 dimensions only, not in 3 dimensions. And when you think of a boat and you have the bow wave of the boat going sideways, you can get crazy ideas what to do with that wave.
The B-47, one of the first military aircraft with the swept wing, had a control problem. At high speeds, the nose would pitch up. The solution proved to be a simple device on the upper surface called a fence or vortex generator. James Osborne of the Boeing Company was the designer. When airplanes became fast enough to pass over from subsonic speed to supersonic speeds, the problems became enormous. NACA's Richard Whitcomb found a solution in something people called the Coke bottle fuselage, or area rule.
The pipe of air that has to get around the wing, it can't change its shape. It can't get smaller to get around the wing. It's a constant area, therefore it has to bend around that wing. Now, where can it go? It probably, in general, gets pushed this way. Well, let's have it come out this way. It gets pushed out this way. And therefore, it continually is pushing more and more pipes out here. None of these pipes can change shape or cross-section. Therefore, any pipe that gets pushed out this way, the piece of pipe right next to it gets pushed out too. And so you go way out here, and these pieces of pipe are all being pushed. So what we do is to essentially neck down the fuselage in this region, make it narrower here, so that we account for the cross-sectional areas of the wing. In other words, we subtract out of the fuselage the area of the wing. Now, with the indented fuselage, that pipe doesn't have to go out this way. It can bend into the hole in the fuselage.
The NACA research program developed the X-1, and on October 14, 1947, Chuck Yeager broke the sound barrier. The Douglas D-558 Phase 1 investigated high-speed flight with a straight wing. Then came the Northrop X-4 and the D-558 Phase 2 with a swept wing flying at transonic and supersonic speeds. The Bell X-5 provided research into wings which had a variable sweep. The Douglas X-3 and then the X-1A provided valuable research flights. The X-2 worked at altitudes above 100,000 feet and beyond Mach 3 before it crashed, killing Mel Abt. The X-1E and the X-1B continued the step-by-step research into higher Mach numbers and thinner air. The next step, the X-15, operating in air so thin that normal aerodynamic controls wouldn't work. Reaction controls were the answer.
We knew the X-15 would look something like this. We knew that it would be a manned aircraft that would fly more than 4,000 miles an hour and as high as 250,000 feet. We knew that like the X-1, the X-15 would be air-launched and propelled on its flight by a rocket motor, the most powerful engine ever installed in an airplane.
Scotty Crossfield, a North American aviation pilot, flew it the first time. Each flight was planned to make the most effective use of this research aircraft as a flying laboratory. Milt Thompson and John McKay, NACA pilots, train on X-15 flight simulators.
Ready to launch. 5, 4, 3, 2, 1.
That's a good light. That's a good light.
Hello on thrust. Give us the chamber reading.
Got 12 degrees.
One flight with McKay at the controls
Chamber pressure.
had engine problems. An emergency landing on Mud Lake was ordered.
Push your throttle up and give us chamber pressure.
We don't have chamber pressure, about 200.
Roger, you got full throttle?
Affirm.
You're running at 30%.
30%? How we doing, Bob?
Roger, you're going by Mud Lake. It looks like a landing at Mud Lake.
Right. Looks from the slope down there like there's a very tiny bit of wind from perhaps south and a little bit east. There's much.
McKay survived the crash, but died years later as a result of the injuries he sustained. The aircraft was repaired in a matter of months. Pete Knight, A. Scott Crossfield, Robert White, Bob Rushworth, Bill Dana, Milt Thompson, Michael Adams, John McKay, Joe Engel, Forrest Peterson, Joe Walker, Neil Armstrong, the X-15 pilots who flew in this joint program with the Navy, Air Force, NACA, and NASA, set records for speed and altitude, Mach 6 and 67 miles up. They were the first men to go into near space. Bill Dana in the last flight of the X-15. It is fall of 1969. In all, 199 flights were made over 9 years. In the 1970s, the competition to build the air fleets of the world challenged our industry. Increased air traffic, crowded airports, noise, pollution, and safety in the air were the problems faced.
The United States has always been able to stay ahead by using technology faster than any other country. Most of the civilized countries know this technology, but they are much slower in getting it from the lab into the airplane.
The B-70 was the result of research in our wind tunnels, in our laboratories, and in the X-model aircraft. The B-70 was capable of supersonic speeds and was considered a forerunner of an American supersonic transport. It crashed in a freak accident during a flight to get publicity photographs with other planes equipped with General Electric engines. Joe Walker, NASA's chief test pilot, flying overhead, clipped the rudder of the B-70. His plane exploded. Our supersonic bomber and transport programs were canceled. Igor Sikorsky, pioneer aircraft designer, speaks of the creative process of aircraft engineering.
Well, certainly, the question of a teamwork entered now to a greater extent than it entered before. And this is both in science and perhaps in every other branch of technique. Nevertheless, I am convinced that the work of the individual still remains a very important factor, still remains a spark which moves mankind ahead, even more than teamwork. Teamwork comes into existence after the spark, the intuitive spark of a living man started something. Then later comes the teamwork to give a bigger body to the little soul which he created. So briefly, to my mind, creative work is still there with us, still there to stay, and still remain a tremendously important factor.
95 miles, .972. I'm going to tap .167B right now.
Research into aircraft structures and safety in the air is an unending research goal in NASA's wind tunnels. Here, the problem is flutter, a phenomenon which can tear an airplane apart. The problem of stall spin has been with aviation since the beginning.
How do you know that the accidents that took place were due to stall spin?
That information came from a special study made by the Air Force because of the concern over this problem and of a joint program which we are engaged in with the Air Force to see if we can eliminate that problem.
In general aviation, The objective is to design an aircraft which will not enter into an inadvertent stall or spin. At NASA's Wallops Island Research Facility, an aircraft is instrumented for spin tests. NASA pilot Jim Patton will fly the test. About 30% of all general aviation fatalities can be traced to stall spin.
2, 3, 4. Seems to be staying fairly steep. 5, 6. Stable. 7. Recovering, and it's responding slowly.
On this research aircraft, when a recovery from a spin can't be made fast enough for safety considerations, a parachute is deployed from the tail to aid recovery. At NASA's Langley Research Center, a series of controlled crash tests look into aircraft structures. And here, a large helicopter fuselage is dropped from 50 feet. Inside are anthropomorphic dummies, instrumented to record the factors which affect passenger survivability. The role of flow phenomena around an airfoil is studied by computer and in the wind tunnel. Of particular interest is the problem of vortex flow around the wingtip. This pattern in the air after large, heavy aircraft results in dangerous conditions for a following light aircraft. The FAA has imposed traffic delays in the landing or takeoff sequence behind jumbo jets. In order to give pilots a better organized cockpit and to provide instruments which are easily viewed, a system of heads-up cockpit displays is being developed. This will aid pilots during instrument approaches to landing in heavy weather. The human factor and the conditions of communication in aircraft operations are studied by NASA and the FAA. The incident of traffic flow on and around airports is shown. Air controller problems involving the relay of vital information to pilots and to controllers taking over a work shift is analyzed. A system providing for the reporting of unsafe conditions, violations of air traffic rules, or other hazards to safety has been instituted. And NASA, the monitoring agency, in 8 years received 37,000 reports. Computer-generated recreations of air accidents reveal the true nature of the complex air movements and point to mechanical and control problems. Lightning can strike aircraft in flight. There has long been discussion as to the dangers involved. Are they real or imagined? NASA flies into severe weather to find the answers. A form of turbulence which can form at high altitudes is known as clear air turbulence. It occurs very often on the eastern slope of the Rocky Mountains. A high-flying jet can suddenly drop hundreds of feet. We want to know how to forecast this condition. Aircraft fire is studied by NASA's Lewis and Ames research centers. The composition of materials within the cabin can cause toxic fumes. There are possibly ways to treat aircraft canopies and windows so they can withstand heat longer. And research into fuselage construction indicates ways to minimize the danger of fire. At NASA's Langley Research Center, aircraft tires become a research focus. There are ways of improving traction and wear. Many aircraft tires are retreaded 7 or 8 times. The use of a synthetic polymer promises to extend the lifetime of aircraft tires. Another promising area for advances in aircraft design involves the work on short-haul aircraft. The modern nation has become transportation dependent upon its fleets of jets to haul passengers and freight over oceans and continents. The large jet transport is not efficient at short distances, nor can it land at small airports. The solution appears to be some type of short-haul aircraft. The XV-15 tilt-rotor aircraft, undergoing research and testing at NASA, has great promise. 2 25-foot prop rotors on the wingtips lift the aircraft like a helicopter and then tilt forward to drive it up to speeds of 350 miles per hour. Aerial photography and a science called remote sensing has proven a boon to civilization in many areas. The use of Landsat satellites for this has provided great progress in the art. High-flying aircraft serve the same purposes, and in many ways they can provide a more flexible result for specialized problems. The U-2 remote sensing aircraft is flown by NASA pilots from locations within the continental United States to provide Earth observation to aid in farming, water conservation, and in describing geological formations. During the St. Helens eruption in the Northwest, photographs from these aircraft caught the start of the volcanic activity and followed the dramatic events. The advances in aviation since the beginning of the century are dramatically represented here in the performance of the Blackbird, the YF-12. The use of materials, the design for speed and altitude are unparalleled in the science today. It flew from New York to London faster than the shadow of the sun. But of all the flights and all of the records set since the beginning, none can stay with the simple achievement of flying across the English Channel in the Gossamer Albatross. On June 12, 1979, Brian Allen made the flight to win the $200,000 prize for the designer, Paul McCready. Contest regulations eliminate any ground crew, help from a motor or propellants, and rule out an air launch. The Gossamer Albatross weighs 70 pounds with a wing spread of 94 feet. In the future, the shape of aviation could include an 8-bladed propeller or an aircraft with a swing wing. There could be advantages in fuel saving and speed. We have come a long way, and it has happened in our time. It is here before us in the Air and Space Museum in Washington, D.C. More than half a century separates the Wright Flyer from the X-15. Here at the Smithsonian, just a few feet brings them together.